In the world of automation, logic is nothing without the power to move. Today, we master the three essential components that bridge the gap: relays, contactors, and solenoids. All three of these components, relays, contactors, and solenoids, share one foundational secret: electromagnetism. When a small electrical current flows through a copper coil, it generates a concentrated magnetic field. This field strength, defined by the physical geometry of the coil and the current, is the invisible bridge between logic and muscle. It allows a safe, low-power control signal from a microchip to physically pull a metal plunger, safely switching a high-power load. Inside a standard relay, the magic happens through a few simple mechanical parts. Let's peel back the casing. At its heart is an electromagnet, a glowing copper coil wrapped around an iron core, paired with a movable metal armature held by a spring. On the switching side, we have three main terminals. First is COM, or common, where your main power source enters the relay. Without any power to the coil, the spring pulls the armature to connect COM to the NC, or normally closed terminal. This path is on by default. When the coil energizes, it creates a magnetic field, pulling the armature down. This breaks the NC connection and snaps it over to the NO, or normally open terminal. Here is the true power of a relay. It acts as an impenetrable bridge between two completely different electrical worlds. On the left, we have our safe, low-power control circuit running on just 5 volts DC from a microcontroller. On the right is our high-power load, a 120-volt AC light bulb that would instantly destroy our delicate electronics. Notice the thick isolation barrier. The 5-volt signal energizes the electromagnet, which physically pulls the switch on the 120-volt side. Because the connection is purely magnetic, the two systems never touch, ensuring total safety for your logic board. To control massive industrial loads with a tiny microcontroller, we must build a specific hardware architecture. This is the complete control loop. It begins at the logic layer, your MCU, outputting a fragile 5-volt signal. But here is the catch. A standard MCU pin can only supply about 20 milliamps of current. A mechanical relay coil needs at least 70 milliamps to magnetize. Connecting them directly will overload and fry your board. That is why we introduce the amplification layer, a transistor or driver circuit. The driver boosts the current, triggering the relay in the control layer, which safely switches the massive high-voltage load without risking your logic board. Now, let's build the control side. We can't connect a microcontroller directly to a relay coil. It draws too much current. Instead, we use an NPN transistor as a switch. First, connect Arduino pin 13 through a current-limiting resistor to the transistor's base. Next, connect the transistor's emitter directly to ground. The collector then connects to the negative terminal of the relay coil. Finally, power the relay coil's positive terminal with 5 volts. Crucially, the Arduino and the relay power supply must share a common ground. Let's look at mistake number 1, forgetting the flyback diode. When you cut power to a relay coil, it doesn't just quietly turn off. The coil is an inductor, and physics dictates that inductors resist sudden changes in current. The collapsing magnetic field generates a massive reverse voltage spike known as back EMF. This spike can easily reach hundreds of volts, instantly destroying your control transistor or microcontroller. The solution? A simple one. N4007 flyback diode placed in reverse parallel with the coil. It safely loops the spike back into the coil until the energy smoothly dissipates. Now for the high-power load side. Think of the relay's internal contacts exactly like a standard mechanical wall switch. To drive a 12-volt DC motor, connect your high-power supply directly to the common or COP terminal. Then, wire the motor to the normally open, or no, terminal. When triggered, the circuit completes and the motor spins. You can also switch AC loads like a mains-powered lamp, but a critical warning, never touch the high-voltage side while the system is live. Now that the hardware is wired, let's look at the software. The beauty of this setup is that controlling a high-power load is exactly like blinking a simple LED. In our Arduino code, we first define the relay pin as an output. Inside the loop, a single command does the heavy lifting, DITREF. Setting the pin to high sends a tiny 5-volt signal to the transistor's base. This acts as a microscopic switch, allowing current to flow through the relay coil. The coil energizes, the magnetic field pulls the armature, and boom, your high-power circuit is live, all from one line of code. We've written the logic, wired the control circuit, and connected the high-power load. Now, watch the system in action. The microcontroller executes our code, sending a 5-volt signal to the transistor. The transistor amplifies it, energizing the relay coil. Listen for the mechanical click. That's the isolation barrier being bridged. And there it is, a seamless bridge from code to physical power, safely spinning our heavy-duty motor. You've protected your circuit with a flyback diode, but 2 fatal mistakes can still destroy your entire system. Mistake number 2, underestimating inrush current. When a motor first starts, it draws 5 to 7 times its rated running current. If your relay is only rated for the normal running current, this massive initial spike will arc, melt the metal, and weld the contacts permanently shut. Mistake number 3, coil voltage mismatch. Supplying an AC voltage to a DC-rated coil, or vice versa, is a recipe for disaster. A DC coil on AC power will rapidly open and close, a destructive phenomenon known as chattering, while an AC coil on DC will quickly overheat and burn out. Always verify your load spikes and coil types against the component specifications before applying power. To wrap up, here is your definitive control components cheat sheet. For the control side, always include a flyback diode for DC coils, use a transistor driver, and match your coil voltage exactly to your supply. For the load side, oversize your contact ratings by at least 2 times for resistive loads and up to 7 times for motors to handle inrush current. Pause and screenshot this slide right now. Keep these rules handy, and you'll never fry a microcontroller or weld a contactor again.